Right, welcome back, and let me start talking a little bit around oxidation numbers, and then we move on to the last bit of the lesson. Now, from what we have already seen previously, can we be able to determine oxidation numbers for certain substances? Say, for example, here in this example, we have sulfur dioxide, and we are asked to find the oxidation number of sulfur here. What we need to know is that when we check SO2 as a molecule, it is neutral. Now, for a neutral molecule, the overall charge, oxidation number, must be 0. So it means when we add the oxidation number of sulfur plus the oxidation number of oxygen, okay, and of course 2 times the oxidation number of oxygen, we should get 0 is the answer. Now, sulfur oxidation number of sulfur plus 2 times, we know that one of oxygen to be -2, all this should give us 0. So in this case, the oxidation number of sulfur should be equal to 2 times -2, it's -4, -4 taken to the other side becomes +4. So the oxidation number of sulfur in SO2 is +4. That's how you find it. And using this, it means you can get a whole lot of others, okay? And of course, taking into consideration all the rules that I showed in the previous section of the lesson. Okay, I don't have time for us to can go through that together. Let's just move on quickly and begin to talk about reaction rates and try to unpack it nicely, making use of graphics. And this is something that you can expect, especially grade 12s in your end of year exams, being able to interpret graphs that talks to rates of reaction. Let's have a look at this one. Rate of reaction and energy changes. Here we've got a chemical reaction, hydrogen peroxide, which is decomposing into water and oxygen in the presence of copper oxide. And copper oxide there is acting as a catalyst for that reaction to take place. Okay, now this axis, the vertical axis here, tells us about the volume of oxygen gas formed. I told you earlier on in the previous lesson, lesson 15, that if a gas evolves in a chemical reaction, we can actually use the accumulation of that gas, the volume of that gas per time, to check on how fast the reaction is taking place. Exactly the same thing happening here. So that is the volume of the gas evolving over the time for that reaction to take place. Now let's try to interpret this. From 0 seconds to 10 seconds, there is how much gas there that has been formed or evolved of oxygen. You will see from there to there, it's 10. So that will mean that every little division here will be a 2. So this will be 10, 12, 14, 16, 18. After 10 seconds, we have got 18 cubic centimeters of oxygen formed. Similarly, we can look at 20 here, the time 20 seconds. At that point, quite easy to see, you can see you've got 30 cubic centimeters of oxygen having been formed. After 30 seconds, you can see you've got about 40 cubic centimeters of gas formed. After 40 seconds, let's look at it. There it is after 40 seconds. I'm trying to show you how you read these graphs here. This will be 42, 44, 46, 48. So after 40 seconds, we have got 48 cubic centimeters of the gas. After 50 seconds, we are somewhere in between 52 and 54. So that is 54, this is 52, in between there. When we come to 60, we are also in between 56, which is 56 there, and 58 there. But something interesting for me begins to happen at time interval 70. Look at it. It is at 58, this point here. 58 cubic centimeters of the oxygen gas formed after the time of 70 seconds has elapsed. And from there, what do we see? We're seeing some leveling up of the graph there. The graph is it's neither going up nor down. What does it mean? So it means our reaction actually ended or stopped when the time was 70 seconds. When the time was 80, we're still seeing it at 58 cubic centimeters. The time is 85 seconds, still at 58 cubic centimeters. Time at 90, still at 58 cubic centimeters. What does that leveling up tell us? It tells us that the reaction stopped happening as from the time 70 seconds onwards. Okay, so what was significant here in terms of time, it's from 0 seconds to 70 seconds. And then you have your reaction getting into completion. Okay, after that, nothing is happening. Right, so that gives us more or less how we can interpret graphs, and we can also draw graphs from there. See you in the next section.